Hi, I'm Leon, and in this talk, I'll show that both feature reliability and prediction performance are important for the interpretation of predictive models. So we know the characteristics of the brain and behavior are interlinked. And there's been considerable interest in using features derived from neuroimaging to predict behavior at an individual level. When building a predictive model, we're normally concerned with two things. Firstly, does the model have good prediction accuracy? And secondly, can we interpret the model to understand the underlying processes in our brain? For this, we often looked at the feature importance of our model. However, when examining feature importance, there's something important that we need to consider: the reliability of the feature importance. To illustrate why, let's assume that we've just built a predictive model from dataset A. We analyze the model and get a vector of feature importances for the purpose of interpretation. Then, if we build a similar model from datasets B and C, and we analyze them again, and we compare the vector of feature importances derived from these three models, how similar will these three vectors be? If they're different, how can we make our interpretations? If dataset A tells us that network A is important when predicting behavior, and dataset B tells us that network B is important when predicting behavior, how can we reconcile these differences? Therefore, in order to make good interpretations of the relationship between brain and behavior, our models need to have good test-retest reliability when we analyze feature importance. A recent study by Tian looked at the reliability of feature importance in predictive models. They analyzed models predicting cognition from resting FC and found that feature importance had a poor reliability. Furthermore, they observed a trade-off between prediction accuracy and feature weight reliability. Therefore, they suggested that for predictive models, focusing on model reliability rather than prediction accuracy could facilitate better understanding of brain behavior associations instead. However, this trade-off between accuracy and generalizability didn't seem too intuitive to us, so we decided to investigate this issue further. I'll address two questions in this talk. Firstly, are there any steps that we can take to maximize the reliability of feature importance across models? And secondly, with all this emphasis on the reliability of feature importance, should we even care about prediction performance at all? To investigate these questions, we used 5,000 participants in the ABCD. For each participant, we computed the functional connectivity using the resting state fMRI data and looked at 36 behaviors. This included 16 cognitive, 9 personality, and 11 mental health scores. Ultimately, we're going to predict each behavior from the resting state FC matrix and extract the feature importance from our predictive model. Since the ABCD is a multi-site study, as a first step, we divide the 5,000 participants into 10 site clusters. We then use a split half validation procedure. What this means is that of the 10 site clusters, 5 sites were randomly selected to train a linear regression model, and the other 5 were used for testing the model. Next, we calculate the accuracy of the model, ACC1. Then we calculate the vector of feature importance values from the entries of the FC matrix, F1. After this, we swap the participants in the training and test set. So now the participants in the previous test set are now used for training, and the participants in the previous training set are now in the test set. We retrain the model again and calculate the accuracy and feature importance again to find ACC2 and F2. This means that ultimately we should have 2 accuracy numbers, and for each method of calculating feature importance, we have 2 vectors describing the importance of each entry of the FC matrix. We then calculate the prediction accuracy as the average of the 2 accuracy numbers, ACC1 and ACC2, and the test-retest reliability of feature importance is computed as the intra-class correlation coefficient of F1 and F2. We repeated this procedure for all 126 possible combinations of the training and test sites. We then looked at 3 ways of calculating feature importance. In the first, we use the regression weights. Secondly, we use the Hopf transform regression weights. And lastly, we use the t-statistics of mass univariate brain behavior association. So let me go through these methods in more detail. Let's first assume that we have a linear regression model. So this model predicts cognition from the entries in the FC matrix. This would then be the formula relating the two variables. The first method that we can use to interpret the model is by examining the regression weights. This simply means looking at the betas for the model. So that's pretty straightforward. The second method that we can use is looking at the Hopf transform feature weights. For this, we simply take the covariance of each brain feature and the predicted behavior for each subject. Lastly, we also look at t-statistics. So this is commonly used to do brain-wide univariate association. To calculate this, we firstly correlate cognition and each brain feature, and we calculate the t-statistic from the correlation value. So for each of these measures, a higher value indicates a stronger relationship, and the negative and positive values indicate the direction of the relationship between brain feature and behavior. We additionally tested the reliability of the models using different sample sizes. So the 5,000 participants were randomly subsampled into smaller sample sizes of 400, 800, 2,000, and 3,000. The split half cross-validation procedure was then repeated for each of these subsample sample sizes. So here are the results. Let's firstly look at the reliability of feature importance for cognition behaviors. Over here on the x-axis, we have the different sample sizes that we looked at, and on the y-axis, we have the reliability in terms of ICC. The blue boxes are for the half transform weights, the orange boxes are for the t-statistics, and the green boxes are for the original regression weights. So the trend with regards to sample size is very clear. For all three interpretation methods, unsurprisingly, reliability always increases with sample size. You can see this trend for the half transform weights, the t-statistics, and the original regression weights. And within each sample size, the half transform regression weights had a higher test-retest reliability compared to the t-statistics of Mass Brain Behavior Association. Also, the t-statistics were always better than the original regression weights. The half transform managed to achieve a good ICC of 0.74 with the full sample size, whereas for the same sample size, the original model weights only achieved an ICC of less than 0.2. Therefore, it's better to interpret a prediction model with the half transform compared to the original regression weights. So far, what we've shown has been consistent to what Tian has shown in her paper. In this study, we additionally look at two other aspects of behavior, personality and mental health. For the personality measures, we see a similar pattern. Number one, the reliability of feature importance always increases with sample size. And number two, half is always the method with the highest test-retest reliability. However, for personality behaviors, the highest ICC is just above 0.5, which is considered a fair test-retest reliability. The results for mental health tell a similar story. The reliability of feature importance increases with sample size, and the half transform regression weights outperforms the other methods. Similar to personality, mental health behaviors only have a fair test-retest reliability of feature importance. To summarize, we have seen across the three aspects of behavior that bigger sample sizes and using the half transform feature weights lead to better test-retest reliability. These results are consistent to those found by Tian. So now let's move on to our second question. Is prediction performance important at all? Let's first look at the relationship between feature importance reliability and prediction accuracy. To do this, we now average the accuracy and ICC over the 126 splits of each behavior and plot a scatter plot. So here on the y-axis, we have the accuracy in terms of correlation, and on the x-axis, we have the reliability in terms of ICC score. Each dot then represents one of the 36 behaviors. Behaviors related to cognition are colored yellow, behaviors related to personality are colored green, and those related to mental health are colored blue. Looking at the results for the half transform weights, we can see that the reliability of feature importance is highly correlated with prediction accuracy. The correlation between accuracy and ICC is 0.74. We see a similar pattern of correlation between accuracy and test-retest reliability for t-statistics also, with a correlation of 0.95. However, it gets even better. For regression weights, the correlation between accuracy and ICC is even higher at 0.98. A correlation of 0.98 is pretty unbelievable. So there are two possibilities. We either have a bug or there's some link between the two variables. So I'll show you that feature importance, reliability, and accuracy are actually mathematically related. But before I talk about the link between reliability and accuracy, I first want to argue that a model with more reliable feature importance does not mean that the interpretation is correct. We should rather be looking at the feature importance error. So what is feature importance error? To define this term, let's first say hypothetically that the true relationship between brain and behavior is described by some ground truth feature importance. We can call this Fg. Fg will be a number of features long vector. So it's important to note that typically Fg is unknown, but let's say somehow we derive it in this case. Then let's take a random data sample S and we train a predictive model and derive the feature importance. So let's call the feature importance we get from this model Fs. We can then define the feature importance error as the average L2 norm of Fg and Fs. What this represents is the average distance between the learned interpretation from each model and the ground truth. And we will see that this term, the feature importance error, has two components. From the feature importance error, we can do a bias variance decomposition, and with a little manipulation, we can find the first term, the L2 norm between Fg and Fs bar. Here, Fs bar represents the average feature importance over the learned samples S. So this term represents the difference between the average interpretation and the ground truth. And you might recognize this second term, it's simply the variance formula. The second term represents the variance between a variance of feature importance learned from the various data samples. This leads to the following implications. Firstly, We can see that a highly reliable model that predicts similar features over many samples should have low variance. In other words, high ICC equals to low variance. However, variance is only one part of feature importance error. In order to have correct interpretation of a model, both high reliability and low bias is required. Otherwise, interpreting feature importance may be reliable, but reliably wrong. Therefore, we need to focus on feature importance error as a whole rather than just the reliability of our model interpretation. For model interpretation. But how can we practically compute feature importance error? In most cases, we don't know the ground truth. In other words, FG is missing from this equation. Fortunately for linear models, we have a good proxy for this because feature importance error is actually linked to prediction accuracy. I'll show you how they are linked in the next part at the top. First, let's assume that we have brain features X and behavior Y, and they have some underlying linear relationship. So Y equals to W, X, WG plus epsilon. So here Y is a scalar representing some behavior. X is the number of feature length vector of brain features. W is a feature length vector of regression weights, and epsilon is some independent noise term. So then, after this, we train our regression model with some data sample S, and we can call the regression weights that we learn from this sample WS. We can do this multiple times with different data samples. And let's first start by looking at the expected prediction error over the different samples that we use to train each model. This can be found by taking the average L2 norm of the true and predicted behavior values and averaging it across all data samples that we use. So after this, we rearrange this equation, and we find that expected prediction error consists of two terms. The first term consists of the variance of the noise term, and since this is noise in the data and out of our control, we call it irreducible error. The second term is the difference between the ground truth weights and the learned weights, WG minus WS, multiplied by some scaling controlled by the covariance of features X. So we call this a transform weights error. Looking at these two components that make up our prediction error, you can see that the transform weights error is the same as the feature importance error that we found earlier. Therefore, since prediction error and feature importance error are directly linked, we can use prediction error as a proxy of feature importance error. So to sum up how the reliability of model weights is related to prediction accuracy, you can see that both reliable weights and decreased weight bias lead to reduced feature importance error, which then leads to reduced prediction error. Therefore, we're able to use prediction error as a direct proxy of correct feature importance when interpreting our models. To summarize this talk, we showed that using the Hopf transform and larger sample sizes, we are able to achieve more reliable model interpretation. And secondly, we showed that feature importance reliability is correlated with prediction accuracy. Furthermore, correct model interpretations require both low bias in the model as well as reliable feature importance. Lastly, for linear models, using prediction accuracy is a better proxy for correct feature importance interpretations as compared to test-retest reliability. We'd like to take a moment to thank our funding sources, and thank you for your attention.